In this video we're going to look at a mass m attracted to a fixed point. So mass m, ma, attracted to a fixed point O. Okay, but the force of attraction is going to be an inverse square law. Okay, so there's the distance r there. So there's a force of attraction there, so we'll just call that Fa, and it's an inverse square law, so the force of attraction is going to be the mass times a constant proportionality times the distance squared. Okay, and we're going to show that this mass here will travel in an elliptical orbit around this fixed point here, O. Okay, so the way we're going to do that is using the idea of the least action. Now we've seen that in previous videos, that if we had a kinetic and potential energy as a constant, okay, so the energy is conserved, okay, so we've got a T plus V is equal to a constant, then we can write down the equation 2T by dt from A to B, and we can say that that there is a value I, and I is stationary. Okay, so that's the principle of least action. Okay, so now we've seen that in a previous video, so if you're unsure where that comes from, if you look at one of the couple of previous videos, you'll see that the derivation of that little equation. So now T here is the potential, the kinetic energy of the system, so we can then write the 2 times integral from A to B over half m v squared by dt. Now that equals our value of I, so we can cancel these out, so we end up with, and I'll take the m out because the m's a constant, okay, so we'll fix the value of the mass. Integral from A to B over v squared by dt. Now what we're going to do is we're going to look at this not in terms of our time t, but in terms of a little displacement ds. Okay, so we can say that the instantaneous velocity is equal to ds by dt. Okay, so it's a small displacement s divided by a small displacement t. So then we can write our v dt is going to equal to our ds. So we can put this into the equation here, so that we've got one v from here and also the dt. So we'll be left with one v there, and we'll have a ds as well. So you're going to have our m integral from A to B over value there, which will be our v ds, and that equals our value of I. Okay. So now what we're going to go and do is we've got to go out and find these values of v and a value of ds, and put it in to the equation here. Okay, so let's go ahead and do that. Okay, so first of all, we're interested in our velocity, but we're interested in velocity with respect to our radius here. Okay, so as the radius changes, how does the radius changes, how does the velocity change? Okay, so that's our question next. So what we want to do then is find v in terms of our radius r. Now we can do that by using finding the potential energy of the system. Okay, so now we can get the potential energy of the system if we use the work energy theorem. So we can say that the change in the potential K is going to equal our force times a distance. Okay, so we should say delta K equals force times a distance. So now in this instance here, the force is not a linear force. The force is a non-linear force. It's given by our it's going to be given by our m mu upon r squared. Okay, and of course the distance here is the distance r. Okay, so we can rewrite that, and we note that in order to, because this is non-linear, we're going to have to find the integral of our force. So integral f and it'll be dot dr. Okay, so the f is going to be given by our m mu upon r squared times dr, and of course the limits of our integration. Well, we note that if we were at an infinite distance away from this point O, the potential energy of the system would be 0. So as we move it closer and closer to this point O, the potential energy of this little bit of mass MA will start increasing. Okay, so what we can do is we can take the limit as r limit from r to infinity. Now we could do it the other way around about. We could go from infinity to r, and it would just be a value of a negative sign in there, but we'll do it like that there just now. So that there is the potential energy in that system there, and that's going to be so our m and our mu are just constants. Okay, so you're just going to end up with a minus 1 upon r whenever you do the integration. Okay, so you have a value of r and a value infinity that is equal to 0. Okay, so that there then is our kinetic energy. So we can then write down that the conservation of energy tells us that our kinetic plus our potential energy is going to be equal some constant. Okay, so that means that we can say that our kinetic energy, if we call it as a half mv squared plus the value of our potential, which is minus m mu upon r equals some constant. I'll just call it c. Okay, so it allows us then to transpose this equation, so you can then say that our v squared equals, well, that's going to be 2 mu upon r plus our 2 times our constant. Okay, I'll just call that constant, big K. I've kept it just to keep it the way I've done it here. Okay, so that's big K, so that's going to mean that our let's see, our v squared can then be written as, now we'll rewrite that there as our mu upon 2 upon r plus 2k upon mu. Okay, so then we can rewrite that then. Let's just get this in this kind of standard form that you see for this derivation. So v squared equals our mu times 2 upon r minus 1 upon a, right? So where a equals, it's going to be equal mu upon 2k. It's actually going to be minus mu upon 2k. Okay, so that there gives us our value for our v, so we can then say that v equals r 2 upon r minus 1 upon a to the power of a half. Okay, so that's one of the things there that we're going to stick in for our value of our v here. And our ds, we're going to do our ds in polar coordinates, so our ds squared, we can say ds squared equals dr squared plus r squared, now d theta squared. Now again, you can see that and derived in previous videos when you look at geodesics on a cylinder and also geodesics in a sphere. You'll see I've derived that. Okay, so if you're not sure about that, you can go back to previous videos. So that then can be rewritten as ds equals 1 plus r squared, and that's going to be d theta by dr all squared, and that's to the power of a half. Okay, so again, these are derived in previous videos. Okay, so it means that what we can do is we can rewrite the equation out. So that's, suppose that's number 2. So we're putting number 1 and number 2 in for v and for ds in here. Okay, so v and a ds there. Now what we'll do here is that's going to be equal to, so our value there is going to be m, and you're going to have that it's going to be a root of mu actually sitting in there, so let's not forget that. M root mu. Now the m root mu, these are just constants, so we're just going to be ignoring them from now on. So we're going to be integrating that. Okay, so it'll be 2 upon r minus 1 upon a, okay, to the power of a half times this thing here. So it's going to be our 1 plus r squared times d theta dr all squared, and that's that whole thing there to the power of a half. Okay, so and that's going to be by our dr. Okay, so that's our equation there, the characteristic equation that we're going to use and we'll be using the Euler-Lagrange in order to work out the values that we require. So and again it's in polar coordinates, so it's going to be over some value 0 to 2 pi. Okay, I'll put that in 0 to 2 pi. Okay, so now we'll note that what we've got here, if we look at it, what we've got here is I there, and I always do this just to kind of work out the work, see the wood for the trees. So I is going to be a function. Well, the independent variable here is our r. Okay, now the dependent variable here is going to be our theta. Okay, but we've only got it's only dependent on theta derivative. Okay, so that's d theta by dr, so we can just call that theta dot. Okay, so we've got a functional that's the independent variable is r, and there's only an explicit variation on the value of our theta derivative. So we can then write down then that we can simplify the Euler-Lagrange. So we'll have partial f by partial theta derivative equals some constant c. Okay, again that's derived in previous videos, so you're unsure how we ended up with that. You know, you can go back to the videos at the beginning of the video series. Okay, so what we do is we'll actually rewrite that, and we rewrite it as c to the power of a half. Okay, so we'll call that the constant. So you can call the constant anything, you know, you call it in any term, so we can call it c to the power of a half because it makes the maths easier whenever you work through the rest of the derivation. So we're looking to do this derivative here. So there's no functionality on the partial on theta derivative in this term here, so that just acts as a constant. So you end up with 2 upon r minus 1 upon a all to the power of a half. Okay, now whenever we do the derivative here, so chain rule for differentiation, so you're going to have a half times what's inside the brackets, 1 plus r squared d theta dr all squared to the power of minus a half, and then differentiate what's inside the brackets. Okay, so inside the brackets you're going to have our r squared, and you're going to have a value of 2, so it's an implicit differentiation, so it's going to be 2 r squared times d theta dr. Okay, so that's us done that differentiation. That can cancel with that, and you're just going to end up with your characteristic, your equation going to be looking like 2 upon r minus 1 upon a to the power of a half times and I'll write it in terms of theta dot, so we're just going to end up with r squared theta dot all upon 1 plus r squared theta dot squared to the power of a half, and again we've defined that as equaling c to the power of a half. Okay, so I'll just work through the rest of it here to get it in the same form as in the booklet. So if we replace this thing here by just call it beta, because we don't want to keep writing it all the time, so we'll end up with beta, and if we square both sides as well, it means we were going to get rid of the power of a half here and the power of a half here, and the top line will be squared. So you end up with beta times, and it's going to be r to the 4 times theta derivative squared all upon 1 plus, it's going to be r squared, and it's going to be theta dot squared. Okay, now the power of half has now disappeared, and that's going to equal some constant c. So you're going to end up with beta r to the 4 theta dot squared equals c, and you're going to have 1 plus r squared theta dot squared. Okay, and then we can take the other across, so you're going to have our beta times r to the 4 theta dot minus r squared theta dot squared times our c equals c. Okay, so I've just taken one of these values across, so you're going to end up with our theta dot squared in the brackets beta squared r to the 4 minus r squared c equals c. Okay, so finally, we're almost there, we'll end up with our theta dot squared equals, we're going to end up with our c upon beta squared r to the 4 minus r squared c. So our theta dot squared is going to equal c upon, now I'll just replace this beta again with the original values. So the original values is 2 pi r minus 1 upon a to the power of, well, times r to the 4 minus r squared c. Almost there, just another couple of lines. So we're going to say then theta dot squared is going to equal, so that's going to be a value of a c. Okay, so we're going to take that a up. Okay, so ac, and that'll be 2ar squared cubed, sorry, that term now 2ar cubed minus r to the 4 minus r squared ac, which equals ac upon, and we'll take out the r squared term, r squared 2ar minus r squared minus ac. And finally, if you can check this and compare this to the equation, and it's in the book, we've got theta dot equals ac to the power of a half all upon r, and that's going to be a r minus r squared minus ac to the power of a half. Okay, it's a bit of a monster. Okay, but that there, you can check that out, it's in the book. Okay, so now I won't bother going through the full integration of this, but we'll give you, because it's similar to a lot of previous ones. So, but I'll give an outline of how it's done. Okay, so I've actually got it here in paper, but you can see the amount of arithmetic that's involved, the algebra that's involved in it. So in order to keep it a little bit simpler, what you can notice is that we use the standard form. Okay, so the standard form for the integral is integral from a to b of minus 1 upon root of a squared minus x squared by dx. Okay, so whenever you integrate that there, you get inverse cos of x upon a. Okay, so we're using that standard form for the integral. Now you've seen that in the previous couple of videos. You've seen it in the derivation of the geodesic on a cylinder and geodesic on a sphere. So we're using the same process. So you can also go back there to see, and also you can use the substitution. If we say that our value u equals c upon r, then you can say that du by dr equals minus c upon r squared. So then you can say that our du equals c upon r squared times dr. Okay, so you can make that substitution. Okay, so you make that substitution into our equation that we've just derived, and you can knock it into this standard form. Okay, so whenever you do that, you knock it in that standard form and you do the integral, you're going to end up with our c upon r equals 1 plus 1 minus c upon a all to the power of a half times our cos of theta plus beta. Okay, so that there is the final equation, okay, that we've been looking to derive since the start. Okay, so and that there is equation. Now if the eccentricity is given by 1 minus c upon a to the power of a half, and it's going to mark out an ellipse or a parabola or a hyperbola depending on the value of a. So if a is positive, infinite, or negative. Okay, so we're going to end up getting a shape something like that round about the origin. Okay, so that's the origin O, and that's the distance r, and that's our mass m. Okay, so thank you for listening, and I'll get you in the next video. Okay, bye bye.